Do you know what happens during an ESD event in a chip? Do you know what are the criterions of a good ESD protector in a chip? Do you know what are all the types of ESD protector devices used in VLSI design? Let's start our journey to know all the answers.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we'll talk about what is ESD. We will go in detail with 2 slides. We have much more detail on ESD. Next, we'll talk about the ESD damage and protection, the general topic, and also we will cover various types of damages that can happen to your chip. Next, we will talk about the qualities of a good ESD protector. Whatever ESD protection we are using, what should be the good criterions for that. Next, we will talk about the ESD protection, whatever done in the VLSI design. That means the VLSI design stage where we incorporate the ESD protection. Next, we will talk about the various ESD protection methodology as per the circuit theory, diodes, stack diodes, etc. Next, we will go in detail for the ESD protection scheme of snapback devices. One of the most popular snapback devices which is used is SCR. Next, we will talk about another snapback device, that is GGNMOS, that is gate grounded NMOS. Finally, we will cover the various ESD protection scheme, that is the type of different clamps that are used for the ESD protection. In today's episode, first we will talk about the ESD damages and qualities of the good ESD protection, and in the next section we will talk about what we do in the VLSI design, and we will go up to the cell level where we use the different devices to protect the ESD, and we will talk about various schemes that are used to protect the ESD. So here we are done with the menu. Let's move forward to the next slide. What is ESD? The most famous type of ESD, that is the large scale lightning, which volts up to 10 to the power 7 volt and currents up to 30 kiloampere. So this phenomena happens in front of your eyes in the rainy season when the lightning strikes. So that is the good example of visible ESD. However, when we are talking about ESD in IC, that is the VLSI, we are talking about the ESD that you cannot visualize, that happens only inside the circuit and at the very miniature level. However, in your day-to-day life, the largest and the biggest ESD, that is the electrostatic discharge, that you can see is the lightning, which has a voltage in order of 10 to the power 7 volt and ampere in order of 30 kiloampere. Now, electrostatic charging of 2 objects result from electron transfer during the friction. So this is the basic physics that happens for a electrostatic charging phenomena. And once any 2 objects are under the friction, they are oppositely charged, and that charge could get discharged through the electrostatic discharge process. Here is our circuit, and you can see here we have various components, like we have transistor, IC, etc. And whenever your body is charged and you touch the device, suddenly that electrostatic zap, that is the discharge, will enter into the entire circuit board, and it may damage your transistor, it may damage the IC or any other component which is susceptible to the electrostatic discharge. ESD is an electrostatic event which balances the charge potential difference between the 2 charged objects of opposite polarity, leads to high current in a very short time. This high current in a very short time we will talk about in next couple of slides, where we will show you the graph. In this slide, we saw the phenomena that actually physically that is occurring here when you are touching any circuit with your bare hand, and that actually does the ESD. So those electronic engineers who actually do this kind of assembling and handling these circuits, they use a electrostatic strap that they tie to their hand and which is connected to the ground, and with maybe in both hands they have 2 different ESD straps, so that the human body is electrostatically protected, so that you're touching any device will not damage. So such kind of electrostatic straps are used in the electronic industry where electronic circuits are packaged and assembled. This is just for your knowledge. On an average, ESD destroys about 20% of electronic components before they are installed into a system. So this is what I was talking about, that wearing an electrostatic strap in the electronic industry helps the circuit to get prevented from the damage. After assembly, anywhere from 33 to 70% digital devices fail soon after consumer purchase because ESD may only damage a component, but it opens the door for the further subsequent damages within brief time during the circuit operation. So ESD has two level of damages. First thing, it damages the circuit. Whenever you are touching this circuit, it may damage this transistor and it may partially damage this IC, maybe this pin or the circuitry which is tied to this pin. As soon as we connect the power to this board and entire circuit is in operation, this IC will fail within maybe few seconds of operation. That means this one gets fully damaged due to the ESD and this get partially, and whichever component is partially damaged can become fully damaged during the circuit operation. So this is the risk of the ESD, and hence in electronic industry people wear electrostatic straps onto their hands so that the circuit which is getting assembled should not catch any ESD damage. We are done with this particular slide. Let's move on to the next slide. Here we are still continuing on the topic what is ESD, and let us go to the next point. A person can acquire charge by simply walking inside a room. Now this is very dangerous. Even you are walking inside a room with the objects that around you, you can get charged electrostatically. When such charged person or object approaches a grounded conductor, for example a pin of a packaged integrated circuit, that is IC, an electrostatic discharge event can occur. This is characterized by high current in order of ampere within few nanoseconds. And here is the graph that I just spoke in last slide. So here this is the transient response of the ESD, because here in this x-axis we have time and in y-axis we have current. Although absolute values I have not marked here, just for your understanding you can see initially there will be a first peak where the entire set of charge getting discharged, and there can be a secondary peak. The secondary peak can also be there. So the circuit may first get a high peak, a sharp peak that injects the charges into the circuit which can damage multiple objects, and there is a secondary peak again which can damage a secondary level damage to maybe the same component or maybe some other component. So this is the typical transient characteristics of the ESD current. A high current density and or electric field, so sorry, here there is a spelling mistake, can damage the conductor, semiconductor and insulator of an IC. So whatever components are there, anything, whether it is a conductor, semiconductor, insulator, they can get damaged to the ESD event that happens within a fraction of a second. A human sensory perception cannot recognize the several thousand volt that is getting discharged through the ESD. So we are not capable of sensing the ESD. That is our incapability. And that's why if you are working in an electronic assembling industry where you are assembling different circuit boards or soldering different circuit boards or any kind of activities that is related to onto the PCB or actual packaging of the circuit, that time you are advisable to wear an electrostatic strap onto your two hands separately so that any of your hand is not electrostatically charged and the circuit on which you are working that should not get damaged. The circuit present inside the IC will tend to be partially damaged or might break down when this high voltage pulse enters. This can happen to the IC whichever we are dealing with inside, which is maybe inside in the PCB or maybe inside the phone that is you are handling. Now there is another thing that you can notice day-to-day things, that whenever you are purchasing a RAM, you are purchasing a hard disk, you get in a bag which is maybe of in a graphite color. So those bags are electrostatic bags. Means those bags are electrostatic proof bags inside which the hard disk or the RAM, all these semiconductor things or maybe the computer equipments, all they are packaged in the electrostatic safe bags. So those are also used in the industry for protection. Those are external protection. However, in today's discussion we will talk about the internal protection. That means a circuit should be internally protected from the external ESD injection. So here we are done with this particular slide. Let's move on to the next slide. ESD damage and protection. So let us talk about ESD damage and protection. ESD in an IC usually start with oxide breakdown through percussion path. So generally there is a MOS structure, right? Metal, oxide and semiconductor structure. So this oxide, right? The ESD enters, right? It will create a zigzag path inside it through which the charge will cross, and this is damaged, and the name of this path is called the percussion path. The high current density damages the semiconductor devices through thin film fusing and filamentation and junction spiking. So all these things happen when the ESD event happens in a semiconductor chip or device, whatever you call. The high electric field, on the other hand, can cause the failure through dielectric breakdown or charge injection. So dielectric means oxide here, and there could be some other dielectric which also can get damaged. Not only the MOS structure, but several other oxides are there to protect the different parts of the IC. Also, those can get damaged. Hence, necessary components are used to protect ESD so that the destruction of a product or a system when touched can be eliminated. That means the inside protection to a circuit is given for the ESD event. However, external protection like ESD straps or ESD protection bags that I have just talked about are provided. Internally, we also provide the mechanism to fight the ESD. Due to this factor, there is a strict packaging, handling and design requirements of suppliers by government and other companies. I have talked about again and again about the different safety measures, which I have just repeated with a point here. Here you can see the typical protection method for the ESD. So here we have diodes here we will talk about later, and you can see there is a clamp, and here is our core of the circuit. Here is our IO pad, VDD pad, and this is our VSS pad, and these are the power rails. These two are power rails. So this way we provide the different mechanism we will explain in later slides. This image is just for your reference, and let's move on to the next point. The right hand side picture shows the typical IO schematics protected by the ESD cells. These are the pads which are actually connected in the IC periphery. And here is our core of the circuit and clamp. So this is kind of typical arrangement that we have in our ESD protection schemes. We are done here. Let's move on to the next slide. Various ESD damages. Junction burnout is caused by the injection of the ESD transient of sufficient energy and duration to force the junction into secondary breakdown. So junction means it could be a PN junction or some other type of junction which can get burned out. Junction burnout is often characterized by high reverse bias leakage current or a total short. It can be characterized by a reverse bias operation of a junction, or it can be simply become a short. Oxide punch through is the major category of the ESD damage. Now, when you are testing any PN diode with a multimeter, if both sides giving the continuity beep, that means that PN junction diode, the junction, that means the P and N junction is short there. Whether it is damaged by ESD or something like that, this is a physical phenomena you can check with your multimeter. Because typically the PN junction should not give a continuity beep in your multimeter. It should give only some value. If it is giving the beep, that means it is short. That means the junction is damaged. So we are talking about such kind of damage here, the junction burnout. Now next point is the oxide punch through is the other major category of the ESD damage. Oxide punch through occurs when an oxide is subjected to ESD pulse of high enough magnitude that can cause the oxide to break down. That means we talked about the percussion path through the oxide. That event will happen and damage the oxide, whether it is the gate oxide or some other oxide. Transient domain of an ESD event, the voltage applied the gate oxide must be very large to initiate oxide breakdown. So here we talk that the gate oxide must be very large to initiate the oxide breakdown. The voltage should be high. So in ESD, that is the voltage is very high and that breaks down the oxide. Metallization burnout is often a secondary effect occurring after the initial junction or the oxide failure take place. So metallization burnout means for the different contacts inside the IC, we have metallization there, metallization contact there. So that can even get metal contact can get burnout. So the metallization burnout occurs if the current flowing through the metal forces temperature to rise due to the I²R calculation high enough to reach the melting point of the metal. Three types of ESD damage we have talked about that can happen inside the chip. That is a junction burnout. The next one is the oxide punch through, and next one is the metallization burnout. So these are existing inside the IC, and this type of damages 1, 2 or 3 can happen due to the ESD. So here we are done talking about the various type of ESD damages that can happen inside the IC. Let's move on to the next slide. Characteristics of good ESD protector. So here in this slide we will talk about what the criterions a good ESD protector could have. That means whatever we are incorporating inside the IC, the characteristics that protection element should bear. The good ESD protection element should have the clamp ESD voltage to shunt the ESD stress count. Good ESD protection element should clamp the ESD voltage to shunt the ESD stress current. Next, it can turn on fast enough. That means there should be no delay so that it can act as a passage rather than if the ESD path keeps this particular element and goes to some other part, it can damage that other part. So this part, whatever protector we are using, that should turn on fast enough. Next, can carry large current, so it should have a high current carrying capability. Next, should have very low turn on resistance and minimum series resistance. So the resistance overall, whether it is a turn on resistance or the series resistance, that should be very, very low. It should occupy minimum area at the bond pad. There are pads we have talked about, right, in the IC fabrication. So it should occupy minimum area there. It should have minimum capacitance. So the capacitance should be minimum. Stand out robust against the numerous pulses. Not only one pulse. If multiple pulse of the ESD coming inside, it should be able to handle all those pulse, or rather it should able to handle the pulse train for the ESD. And finally, it should not interfere with the IC's function or the testing of the IC. That means the functional testing. This should be the typical criteria, a good ESD protection element that is getting incorporated inside your chip that should have. So here we are done. Let's move on to the next slide. ESD protection in VLSI design. Here we talk about the different VLSI steps that we do. First we start here the ESD design rules. So generally we have a physical verification stage where we check the design rules. There we incorporate the ESD design rules comes as with the ESD document. The protection design implementation becomes complicated for various IO signal configuration. Also, placement of unrelated circuits near an IO pad causes unexpected current paths through interaction or may render protection device ineffective. So these are checks that should be done by the designer, and the rules may have some of them incorporated. The same could occur in the internal connection between power supplies, preventing the power supply clamp from operating. All of these issues are covered in ESD design documents so that the product ESD design is addressed properly from the very beginning. All these things should be covered either manually or should be through the rules, the design rules. Whatever DRC engine that you are using, that should be able to check these things. ESD protection is done using several types of IO cells such as digital IO buffers, provide high drive up level shifting output, provide down level shifting, and ESD protection for input. So digital IO buffers are there to protect from ESD, and also we have analog IO cells, provide ESD protected analog input out. Two different kind of circuits we generally have, digital and analog, and for both of them we have different type of ESD protection elements in VLSI. So here we are done for our basic VLSI checking step that is there in the VLSI design flow in the design rule check part, and there we check for the electrostatic discharge checking design rules. We're done here with this particular slide. Let's move on to the next slide. ESD protection methodology. The main goal of ESD protection circuits is to provide a low resistive discharge path. We have talked about in the criterion of a good ESD protector. So this we have already talked about. Now here is our typical drawing of various ESD protection unit. Here we are using the clamp. Earlier there was diode, and here is the clamp between the power rails. And this is our pad, an IO pad, VSS pad and VDD pad, and these are our power rails. Figure shows the typical chip level ESD protection scheme in which an ESD power supply clamp is connected between two power rails under the different places. So this is ESD clamp, this is ESD clamp, this is for the VSS and this is for the VDD. We have different type of clamps connected different elsewhere. We'll go in detail, but however this is just for your FYI purpose. The ESD clamp provides the discharge path for an ESD event that happens between two power rails. So here is a spelling mistake. It is happens, not happens. Clamps should be of category of static clamps and transient clamps. Clamps could be two kind of different type of circuit operation. One is a static, another is the transient, based on the nature of the operation. The static ESD clamps turn on once the voltage across the supply rails exceed triggering voltage and start conducting the current of an ESD event. So this is the static, and it detects the two rails and accordingly it acts. The transient ESD clamp take advantage of the rapid change in the voltage during an ESD event to trigger the clamp using a rise time detector and a delay element to keep the clamping element on during the entire ESD event which is happening. So the static clamp acts in a different way and the transient clamp acts in a different way. Transient clamps acts during a circuit operation and the static one acts based on the power rails, the voltages in the power rails. If there is a danger level, it starts acting, and in the transient, during the transient operation, if there is a danger level, it acts at that point. Transient clamps are able to react fast. However, these circuits must be carefully designed to keep their leakage to minimum. So this is another design need because most of the devices now handle and battery operated. So the leakage should be minimum. That is our expectation. So here we talked about the ESD protection methodology, specifically static clamps and transient clamps we have talked about here. Let's move on to the next slide. ESD protection scheme diodes. Turn-on type device, that is the Zener diode. A turn-on type device like a Zener diode turns on after reaching a particular triggering voltage. Once the device is turned on, it offers a low impedance path for the ESD current to flow. The current voltage characteristics for such a device is shown in figure. So this is your typical Zener operation forward bias. Here we are not talking about the forward bias. We are focusing on the reverse bias, and you can see if we draw a perpendicular, right here we draw a perpendicular at this particular VZ. We generally this as VZ. At that particular VZ, that breakdown will happen, right? At this point, it will offer a path where huge amount of current can pass on. So you can see I is here, minus I is here, and this type of protection scheme can be used in a typical ESD protection layer where the level is characterized by VZ of the Zener diode. So you know, right? Even in our analog circuitry, different Zener diodes are available with different voltages. So VZ is not a fixed one or not a fixed value. It can be varying according to circuit design. Such Zener diodes could be placed and they can act as a ESD protector. So here how we place the Zener diode, we place like the diodes are shown here in between the pads, right? The VDD pad, IO pad and the VSS pad. One is connected towards the VDD and another one is connected towards the VSS. So this way we can place them. Diodes offer a simple and effective turn-on type ESD protection. They can be used either forward biased or reverse biased configuration since diode have IV characteristics as shown in the figure. So even if we have some requirements where this forward biased voltage is needed for that triggering voltage, we can also use that. So this is we mark it VI and this is VZ. So based on the need, we can either use in the forward biased VI voltage or VZ voltage depending upon whatever our circuit requirement is there. They offer a very low resistance path, you know, right? Whenever this is going high, this because here the voltage remains fixed and the current goes up, and here the same thing, here voltage remains fixed and the current goes high. Obviously in the negative I axis I'm talking about, hence it's a very low resistive path because the R is very less because the I shoots in here because this is a semiconductor. The advantages of this method, it can be simulated using the SPICE. So you can use your SPICE simulation program to check this kind of operation. One limitation is that the fixed diode turn-on voltage, which can reduce the application of the diode for this. We have a limitation that we can use fixed level of voltage. I have just talked about based on the design, you have to give a fixed voltage. If you are using the forward voltage here or you are using the reverse voltage here, whatever, this is fixed. You cannot change it. It's not dynamic. It's very static. This is the limitation. So here we have talked about diodes. We are done here. Let's move on to the next slide. Stacked diodes. So here we will talk about the next level of application of the diodes. That is, figure shows the ESD protection structure consisting of stacked diodes. So here you can see instead of single diode, we can stack diodes for our better protection. So this can be used. Under normal operating condition, diodes are reverse biased and hence in the off state. During an ESD event, the diode forward bias and divert the ESD induced current away from the internal circuit. The drawbacks of such structure include the relatively large on-state resistance and added complexity in optimizing the interconnect metallization parasitic for advanced CMOS process technology. So this is the drawback here we talked about in the fourth point. However, we can use stacked diode instead of single diode. In that, what will happen? So the voltages will be getting added. So VI or VZ, whatever is there, it will get added and accordingly the voltage will change. So this is the thing that we can also use stacked diodes. In some cases of the VLSI, the stacked diodes are also used. So we are done talking here. Let's move on to the next slide. ESD protection schemes, the snapback devices. Snapback type device. So the snapback type protection schemes are capable of handling very high current. So here you can see we have a SCR put here, a PNPN structure here. Rest of the circuit looks very familiar to you. Already talked about. We have two diodes here and we have a SCR here. And rest of the circuit is V8 VDD pad, IO pad, VSS pad and our power clamp. And this is the core of our circuit. Everything remains same. But here we are using a SCR here. You can see PNPN structure. Gate grounded NMOS, GGNMOS and gate coupled NMOS, GCNMOS and SCR, that is silicon control rectifier, are ESD protection devices which work based on the snapback mechanism. So in the SCR slide we show you the graph that whatever snapback means. Now let us see what type of SCRs are used here. 5 different types of SCR are used for ESD protection. Low voltage triggered SCR, that is LVT SCR. Gate coupled LVT SCR. So we have another type of LVT SCR here. Substrate triggered SCR, that is ST SCR. We have double triggered SCR, DT SCR. And we have boundary MOS triggered SCR. So all these type of SCRs can be used in your ESD protection type. So you can see the ESD protection itself is a very big science here that we apply as a technology in our VLSI technology. So here we are done with this particular slide. Let's move on to the next slide. Silicon control rectifier. So let us talk about the SCR here, whatever property of SCR we are dealing with and how it is getting used as a ESD protector. SCR which provides high value of area gain factor compared to other protection structures. So here you can see the IV characteristics. Here is the voltage and here is the current, and you can see the graph goes like this, and on certain point Vs the control snaps back to this point and it goes in a very high value current. So that means the voltage actually drops and then the current goes high. So here it gives a path for the current to pass on at a lower voltage, and it's almost here we have like this, but in actual practice you can see this will be almost a line parallel to this current I axis, the current axis. Here is the kind of representation of the PNPN SCR structure, that is PNPN. We have anode and cathode and gate here, and here is the BJT equivalent of this circuit. In theory, we also deal with the BJT equivalence, and that's why I have just given this particular schematic here, although it is not very important right now for our discussion, but just for your knowledge, we have posted it here. SCR is commonly used for ESD protection in advanced process technology. However, a SCR has triggering voltage of approximately 20 volt compared to low holding voltage like 1 to 2 volt. This volt is 1 to 2 volt and this is around 20 volt. So this is triggering happens at 20 volt and it snaps back and the voltage goes back to here and it's 1 to 2 volt and high current flows. So this is the beauty of SCR. SCR is popular for its area efficiency. With the same ESD protection level, SCR occupies smallest area among 3 basic devices. The area efficiency for SCR is very good, and that is we need because in VLSI we need the power, performance and area optimization. So we have an entire episode on PPA. You can go ahead and watch that. And also we have talked detail of the SCR operation in the latch up episode. I have provided the links of these 2 videos in the description. You can go ahead and watch in case you have some interest on. The cross schematic view and the equivalent circuit of the SCR is shown in the figure, in which the consisting PNPN structure. After trigger, the SCR will exhibit snapback IV characteristics as shown. So here we have shown after the triggering, right? Triggering happens at that point and then it snaps back and the current goes high. So this you can see this happens actually during the SCR operation, acting as a ESD protector. Typically, SCR has large snapback. So that is what we told, right? 20 volt is a trigger and snapback voltage is 1 to 2 volt. So there is a large snapback here. Gate grounded NMOS, GGNMOS. To solve the ESD problem, GGNMOS, that is gate grounded NMOS, is commonly used for protection device. Here is the kind of schematic that we are using. Here you can see the GGNMOS, the NMOS is here. You can see the source drain is here, and you can see we have grounded the gate here. So this structure acts as a gate grounded NMOS. Rest of the circuit you are very familiar. We have displayed it couple of times from the beginning of this particular video. GGNMOS is easy to design and it is perfectly compatible with PMOS process. However, it consumes relatively large silicon area because of the low current driving capability. So this is the comparison to the SCR, where the area is efficient. Here the area is inefficient of the GGNMOS. Although it is a snapback device, due to GGNMOS has simple structure and it is compatible with the CMOS technology, it is also a popular device for ESD protection. GGNMOS is modified form of the normal NMOS device, as we can see here from the schematic. In GGNMOS, the drain of the NMOS serves as the anode and the shorted gate source and the body contact are tied together to serve as a cathode. This is the structure you can see from the schematics, and this is very simple to understand. We are done here. Let's move on to the next slide. ESD protection scheme. Now we talk about the different clamps. ESD protection circuit. There are different on-chip protection methods are used for ESD protection. The rail-based protection circuit is one of them. Rail-based means which is connected to the power rails directly. Placement of the power supply clamps determines the effectiveness of the I/O protection of the rail-based ESD protection. So clamps are generally used for clamping purpose in between the rails, at least one of the rails. Here you can see this is a schematic of a VDD clamp, and here you can see that this is a schematic of a VSS clamp. So these are the two different circuits. So let me clean up and let me draw a line in between. So this one is VDD clamp, that you can see it's connected with the VDD and also with that ground. For the VSS clamp, if we need for the VSS only, here the clamp is and this one is missing here. These are the two circuits. Power clamp. Power clamps are present inside each power supply I/O. So you can see that pads are here and where the clamps are connected. Power clamps, basically you're talking about this, or this, not about this one. This is a power clamp we are not talking about. They are used to shunt current to the ground from power supply lines when an ESD event occurs or any event which can potentially damage the electronic component. So we are talking about this because here as soon as if it is reaches right, this is the core of the circuit and this is clamp is for different purpose, but this will protect your chip, whatever things are coming from the pad. That means your human count. The RC triggered power clamp is a simple and efficient implementation of the archive of the same. We also have RC implemented power clamps also there. So these are the power clamps we have talked about. There are two type of schemes are there, VDD clamp and the VSS clamp. We have shown both schematics here. And so far we have discussed so many things on the ESD today in this episode. So we are done here with this particular slide. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below. And bye for today.